Classification of hydrocarbons. Hydrocarbons are compounds which contain only carbons and hydrogens, and they can be classified under two different heads, aliphatic and aromatic. Aliphatic hydrocarbons can be further classified as saturated hydrocarbons and unsaturated hydrocarbons. Saturated hydrocarbons are going to be having only single bonds, whereas unsaturated hydrocarbons can have double or triple bonds. Alkanes are examples of saturated hydrocarbons, whereas alkenes and alkynes are examples of unsaturated hydrocarbons. When you say alkenes, it's going to have double bonds. So this is going to have double bonds, whereas alkynes are going to have triple bonds. And each one of these, alkanes, alkenes, and alkynes, can be further classified as acyclic and cyclic. When you say acyclic, this is going to apply to open chain structures, which means there is not a ring structure present. Let's take a look at some examples and also the general formula for each of these compounds. The general formula for acyclic alkanes is CnH2n plus 2. Let's take the example of pentane. So here is an example for acyclic alkane. This is pentane. And let's count the number of carbons here. We do have 5 carbons here. So let's keep n equals 5 and apply it in this general formula. So n equals 5. So C5 and then H2 times of 5 plus 2. Right? So that would be equivalent to C5H12. So this compound should have a total of 5 carbons, right, and 12 hydrogens. Let's count the total number of hydrogens. So 3, 5, 7, 9, and 12. Yes, we do have totally 12 hydrogens. When it comes to acyclic alkenes, they're going to have the general formula of CnH2n. So which means they are going to have 2 hydrogens less compared to the case of alkanes. Let's take an example here. Let's take propene as the example. So here is propene. Now if I'm going to keep n equals 3 here, because I do see 3 carbons here, and apply that in this general formula, let's see what we are going to get. C3H2n times 3, which is equivalent to C3H6. That should be the formula for this compound. Yes, we do have 3 carbons. And then hydrogens, 3 plus 1, 4, 5, 6. We do have 6 hydrogens. When it comes to acyclic alkynes, it's going to have another 2 hydrogens less. So it will be CnH2n minus 2. So take a look into this. We have 2 hydrogens less compared to the case of alkanes. And then here we have again another 2 hydrogens less compared to that of alkenes. Let's take butane as the example. So here is butane. When you apply n equals 4 here in the formula, let's see, Cn, which is C4, H2 times of n would be 8 minus 2. So that would be C4, H8 minus 2, that would be 6. So C4H6 should be the formula for it. Let's calculate the number of carbons and hydrogens in this compound. We do have 4 carbons. And then hydrogens, so 3 plus 2, 5, and then 6. There are totally 6 hydrogens. Yes, the equation is, yes, the formula is solved. And you can take any random compound. Say, for example, here instead of pentane, you can take hexane and find out whether it is aligned with this general formula. Now, in the case of cyclic alkanes, it's going to have 2 hydrogens less compared to that of the acyclic alkane. So it would be CnH2n. And here in this case, it would be CnH2n minus 2. And then here it would be CnH2n minus 4. This would be the general formula for the cyclic compounds. Okay, so when you move from acyclic compounds to cyclic compounds, there will be 2 hydrogens less. Take a look into this. 2n plus 2. Here it is only 2n. 2n, 2n minus 2. 2n minus 2. And then this is going to be 2n minus 4. Now here are some examples for it. So this is an example for an acyclic alkane. This is cyclohexane. So at each of this intersection, you're going to have a carbon, right? And then each of these carbons is going to have 2 hydrogens. Here is an example for a cyclic alkene, where you can see that there is a double bond between these 2 carbons and there is a cyclic structure. And here is an example for a cyclic alkyne, where you can see that there is a triple bond and there is a cyclic structure. When it comes to aromatic compounds, they're always going to be unsaturated, meaning that they are definitely going to have double bonds that follow aromaticity, and they're always going to be cyclic. One great example would be benzene. So benzene is an aromatic compound, and as you can see from the structure, yes, this is cyclic, which means it is a ring compound, and also it has got double bonds, so therefore this is going to be unsaturated. This is again another example for aromatic compound, which is naphthalene. So in all of these compounds, you could see that there are only carbons and hydrogens. So take a look at this. We only have carbons and hydrogens, right? So these are carbons, and then of course each of these carbons is attached to one hydrogen.